Hi, I'm Zhaoheng from University of Southern California. I'm here to present our paper, CAILA, Concept-Aware Intra-Layer Adapters for Compositional Zero-Shot Learning. This paper is authored by me, Haidong, and Professor Nevatia. Let's talk about the task first. In this paper, we investigate the problem of compositional zero-shot learning, which is CGSL. CGSL requires models to recognize novel compositions whose components are already known, more specifically attributes and objects. Here's an example. Attributes large, object bear are known from large bear, while attributes old and object castle are known from old castle, and the model is required to combine these concepts in a different way and recognize large castles and old bears. So here's our motivation. As we mentioned before, CGSL requires task-specific designs for optimal performance, but its zero-shot property requires models to be robust to overfitting. Recent work starts leveraging the knowledge from vision language pre-trained models like CLIP for the CGSL task. However, previous work only treats CLIP as a black box and lacks task-specific design. For example, prompt learning only learns the part of the word embedding, while CLIP adapters add simple MLPs at the end of each encoder. Thus, we propose CAILA, a framework with concept-specific adapter inside the CLIP model for better CGSL understanding. Here's an overview of our method, CAILA. First, we create concept-aware encoding blocks for both text and images, and the awareness are implemented through adapters. We further fuse such concept-specific knowledge through the mixture of adapter mechanism. This is a zoom in of each concept-aware transformer block in our model. We follow the standard adapter design with downsample and upsample operations, and adapters are inserted after self-attention layer and the feed-forward network as what they has been done in the regular adapter design. And in our model, each transformer layer has one independent adapter for each concept. Let's talk about the MOA, mixture of adapters. We perform MOA on both vision and language side. With text, we simply average outputs of each text encoders. And for the vision encoder, we perform aggregation on each layers of adapters. And such aggregation is done on both the output of the adapter and with the intermediate representations of the outputs. As we can see in the figure here, the average is done with the ZA, ZC, and ZO during the inside the adapter, and the outputs of these adapters are being averaged again to create the final output hidden state edge. So given the concept awareness of our model, now we are able to extract concept-specific features from images. This enables us to perform a so-called concept shift. So here's an example. We extract melted from an image of melted butter and the object candy from another image of pressed candy. So now we have the attribute-specific feature of melted and the object-specific feature of candy. We're able to combine them through the vision MOA mechanism, and then we will get a new feature of melted candy. And then we can use this to align with the corresponding text embedding of melted candy, which will bring us extra diversity of the training data and increase the robustness of our model. Here's the experiment setup. We evaluate our model on 4 datasets. The first one is MIT states, which has 115 attributes and 245 objects. As pairs, it has 1,000 sim pairs for training and 400 unseen pairs for testing. Another dataset is C-GQA, which has 453 attributes and 870 objects which is a much bigger set than MIT State's. So here it has 7,000 pairs for training and 1,000 pairs for testing. We also test on a fine-grained shoe classification task dataset called UT-Zappos. It has 16 attributes and 12 objects. And it has 83 pairs for training and 18 pairs for testing. At the end, it's the hardest task that that CAILA has been worked with is the VAW-CZSL, which has 440 attributes and 541 objects. In total, it has 10,000 seen pairs and 2,500 unseen pairs. So we evaluate our model in two scenarios, closed world and open world. In closed world, the target pairs are given, and thus is a limited vocabulary of pairs, while in open world, the target category can be any possible combinations, making the search space essentially of a size with the number of attributes times the number of objects, which is much bigger than the closed world. For evaluation metric, we take AUC, area under curve, of the seen-unseen accuracy with the bias as the main metric, and then we also report the best harmonic mean on this curve and best seen, best unseen accuracy on the same curve. So here's the performance in closed world with our proposed CAILA model. We can see that our model outperforms other baselines by large margins on all datasets. Specifically on MIT States, our model achieves 23.4, which is 2.8 higher than our baseline model, and our model achieves even bigger improvement with C-GQA. On C-GQA, our model achieves nearly 50% relative improvement compared with the best baseline model. And we also observe similar improvements on UT-Zappos and VAW-CZSL on not only the main metric, but with other evaluation metrics. Here is the result of our model in the open world, and we can see that the performance of our model is consistent with what we have observed in the closed world. That our model improves the baseline by 1.4% on MIT States, and 0.6% on C-GQA, and 2.5% on UT-Zappos. Here is the ablation study, which we try a number of settings in exploration of what's the best setup for adapters, MOA, and how the mixture can be done on the vision side. And these results reveal that the best way to perform CZSL with our model is to leverage adapter and MOA mechanism in both modalities. And on the vision side, the vision mixture of adapters works better with our proposed design that's been discussed before. Thank you for watching. If you would like to learn more of our paper, please feel free to scan this QR code for the paper or drop by during the post session. Thank you.